In this video, I want to show you how to calculate simple beams and how to determine the internal forces in these beams and draw the graphs of these forces. This will be a video for people who are just starting their journey with beams and who want to learn how to draw internal force graphs. Therefore, this is part 1. I will record part 2 in which I will show how to quickly compute beams and how to quickly draw internal force graphs. Okay, so let's get started. Example 1. Calculate and draw the internal force graphs. We have a simple beam supported here by a pin support that does not move, here by a movable pin support, and it is only loaded by 2 transverse forces to the beam. We need to calculate and draw the internal force graphs. Let's mark it. Here are already marked lengths of the individual sections, 2 meters, 3 meters, 3 meters. Let's designate them as A, B, C, D. And we need to know that in the fixed pin support, we have 2 reactions, a horizontal component and a vertical component. In the movable pin support, we have one reaction that is perpendicular to the direction of movement. So if this support were at an angle, let's say, the reaction would be perpendicular to the direction of movement. So in our case, it looks like this. I labeled ha and va for horizontal and vertical. You can label rax, ray arbitrarily. So now the equations of static equilibrium. To calculate the reactions in our beam, the support reactions, we will use static equilibrium by summing projections in the x direction, summing projections in the y direction, and summing moments about any point of our beam. So we can start with the sum of projections on the x-axis, looking at which forces act in the horizontal direction. Here in our system, it is only the reaction ha, so ha equals 0, there is no other force. So we have already calculated one component of the reaction at this pin support. Next, we can do the sum of moments at any point. In practice, we will either do it at point A or at point D, because at the point where we sum the moments, if the reaction or force passes through the pole, for which we are summing moments, it does not create a moment, so we do not include it in the equation because the moment is force times arm. So forces that pass through the moment pole do not act on any arm, and thus do not appear in the equation. Therefore, if we do the sum of moments at point A, then we will not see, well, there will be no va force or ha force in this equation, because they pass through the pole of the moment, so there will only be the VD reaction that we need to calculate. And if we do the sum of moments with respect to point D, then there will be no VD force in this equation. There will only be the VA force, and those 2 forces acting on the beam. I will calculate the sum of moments about point A, so the sum of moments about point A is equal to 0. Now, va and ha pass through the pole of the moment, do not create a moment. Then we assume, when calculating reactions, we still have some freedom. I assume that, for me, right-hand moments are positive moments. One can assume that left-hand moments are positive. Here, there is a freedom of choice. I assume that right-hand moments are positive, so this 10 with respect to the pole of moment A would like to twist clockwise, as I show. This 10 with respect to the pole of moment A would like to twist clockwise, so it is positive and it acts on the arm. The arm of the force action is the shortest, that is, the perpendicular distance from the direction of the force action to the pole of the moment. Here, well, in beams, this is nothing difficult. When we have some more complex systems, some frames, bar frame arrangements, something like that, well then, when these forces are at an angle, we have to think a bit here. But we simply have shear forces. So the arm of action is nothing other than those 2 meters, that is 10 clockwise times 2 meters. Add the 15 also clockwise, the arm of action of 5 meters, and subtract the reaction VD on the arm of 8 meters. VD is negative because it is counterclockwise. It equals 0, and from this we can calculate the reaction VD, which amounts to 11.875 kilonewtons. I did not write in the problem statement that these are kilonewtons, but generally we encounter such orders of magnitude in beams, so these are kilonewtons. Okay, so we have the sum of projections on the y-axis, which is the vertical axis, and we look at the left side. Force via acts upwards, so for us it is positive. We can also freely assume here, but it is usually taken as I say. So V upwards is positive, 10 downwards, the direction is downwards, so it is minus 10, minus 15, VD upwards, that is, plus VD. We have calculated VD, so we substitute it into the equation and calculate VA, which amounts to 13.125 kilonewtons. So we have calculated the support reactions, which means we can now divide the beam into segments, as indicated in the drawing. We have 3 segments. And we will write the conditions of static equilibrium for the cut sections of the beam, which means we will be doing mental cross-sections. Thus, we will obtain equations describing the values of shear forces and bending moments for our beam. So we will have 3 segments, as the beam is indeed divided. The first segment will be the segment AB. And one more verification, excuse me. We can perform another verification. The verification can be the sum of moments. We can do it at any point. So we will do this at a point through which no reaction passes, meaning we can either do it at point B or point C, let's say. Well, at any point for that matter, we can do it. I will do the sum of moments at point B, and this sum of moments must be equal to 0. If it is not equal, it means we calculated the reactions wrong. So the force VA acts at an arm of 2 meters, clockwise relative to pole B, so positively. VA times 2 meters, then 15, acts clockwise, which is also positive at an arm of 3 meters. And VD at an arm of 6 meters acts negatively, that is minus VD times 6 meters. When we substitute the calculated values, it will indeed come out as 0 equals 0, meaning the left equals the right, so the reactions are calculated correctly. So at this point, we can check and be sure whether the reactions are calculated correctly or incorrectly. If the reactions are calculated incorrectly, there's no point in continuing with this task, because if the reactions are calculated wrong, then the rest, that is the internal forces, will be calculated incorrectly and the graphs drawn inadequately. So it is worth checking here. And having this certainty that we have the reactions calculated correctly, we can divide the beam into segments where the loading method will change, and we will write the conditions of static equilibrium for the cut parts of the beam. And in this way, we will receive equations describing the values of shear forces and bending moments in specific segments, and then we will be able to draw graphs of shear forces and bending moments. So, the first segment AB is the segment from 0 to 2 meters, meaning x1 is from 0 to 2 meters. And we can imagine, at the beginning, we can still make auxiliary drawings. I will for now create these auxiliary drawings, but generally we make a mental cut of this beam in the segment from 0 to 2 meters. So we are covering the right part of the beam. We do not see the right part of the beam, we only see what is on the left side. The reaction HA is 0. So we only see the reaction VA. We do not see that 10 yet. We are infinitely close to it, but we do not reach it. So we are in the segment from 0 to 2 meters, making a mental cross-section. We see such a part of the beam looking from the left side. And for this cut part of the beam, we write the equation for the shear force. So what is here is only the force VA. So the shear force I will denote as Q in segment AB. Depending on the change in x1, here this shear force will actually not depend, but that's how it is written. It is simply VA, positive, because it acts upwards. So now we check at the beginning of the segment, meaning we substitute 0 for x1 and substitute the beginning and end of the segment, meaning 0 and 2. But this equation is not dependent on the change in x1, so if we substitute 0, it will simply be VA, which was previously calculated as 13.125 kN, and if we substitute 2, that is 2 meters, then it is the same amount. Well, now we need to draw it. Now we need to write the moment equation for this cut part of the beam, that is, for the system as drawn, as if we wanted to write the moment equation for this pole. So we would have VA acting clockwise on the arm, and the length of this cut part of the beam is like a variable x1, so this force acts on the arm x1. Thus, the moment in the interval AB from x1 is VA times x1, positive, because it's clockwise. And now just like that, we substitute x1 with 0 once, and then with 2, and calculate the value. If we substitute 0, then VA times 0 is 0, And if we substitute 2, then 2 times VA is 26.25 kN times meter, which is the unit of moment. So we have calculated the values of shear forces and moments in the first interval AB. Now we move to the second interval, which again is the interval BC from 2 to 5 meters. So it's as if our coordinate system starts here from the left side at the beginning of the beam. And now the interval BC is from 2 to 5 meters, so x2 ranges from 2 to 5. So we are somewhere in this interval, and we start from the left side again, covering the part of the beam that is on the right side. So this time we already see the 10, but we do not see the 15 yet. So we are now infinitely close to this 15, but we do not see it. We see what is on the left side, so reaction HA is 0. I do not draw it here. Reaction VA acts upwards and 10 downwards. And now for this state, we need to write the equation for shear forces and the equation for moments. So QBC, that is the shear force in the interval BC from x2, we have two forces here. Virginia acting upwards, thus positively, and 10 acting downwards, thus negatively. So it is simply VA 10. By substituting for x2, the beginning and end of the interval, that is 2 and 5, since this equation is independent of variable x2, it will be a constant value, which is 13.125 minus 10, thus 3.125 kN. And the same goes for the moment. The moment in the interval BC, we would like to create a moment equation as if there were a pole here, thus being at length x2, which is in the interval from 2 to 5. So the reaction VA rotates clockwise, thus positively, on the arm over the entire length of the interval, thus times x2, and now 10 definitely rotates counterclockwise relative to this pole, meaning negatively. Now at what range it acts might initially seem difficult to write down, but let's consider, if the entire interval we have here mentally cut out, if the entire interval is the length x2, which is a variable ranging from 2 to 5 meters, and we know that the distance between VA and 10, even looking here, is 2 meters, well, since it is 2 meters and this is some variable x2, then this value, thus the arm of the force, 10, relative to this pole here, thus this length, is x2, thus the entire length minus this 2, x2 minus 2, simply. So the moment in the interval BC is VA clockwise times x2, thus the entire interval, minus 10 times x2 minus 2. So we substitute the start and end of the interval, which is 2 and 5 meters for x2. When we substitute 2, it cancels out to 0. We get 26.25 kNm. When we substitute 5, we simply substitute the value of 5 for x2 into the equation we wrote, and we calculate the result, which comes out to 35.625 kNm. So we already have two intervals behind us. The third interval remains, and now I would like to show you two ways to calculate this third interval. Well, we can either make intervals 3 times from the left side, so the first interval from 0 to 2, the second interval from 2 to 5, and the third interval from 5 to 8. So we can see we make such a cut, we only see the reaction VA, as we had here. The second time we make a cut here, we see VA and 10, and the third cut we could also make from the left side. And we will do that shortly, so we would see these three forces. But it is worth at least once to go from the right side and make a look from the right side of this interval, as if here we start the coordinate system from 0 to 3. From 0 to 3, so this time, and I will do it shortly, we would cut this beam in the opposite direction and cover its left part, so we will only see this reaction, VD. So we cut the beam, cover its left part, cut the beam somewhere in the range from 0 to 3, and cut it, and cover the left part. We only see what is on the right side. I will show you how this looks in practice shortly. So I will show you the difference, why it is worth at least once, because sometimes it's not worth counting 3 times from the left side, because we see more and more forces, so these equations are getting longer and more calculations. But if we go from the right side, I think we will have more than half the calculations less. Okay, so first I will do it as before. That is from the left side, interval CD from the left side. So I cover the right side again and see all the forces that are from the left side. So we now have this 15. This interval is from x3 from 5 to 8. So the shear force in the interval CD, that is QCD from x3, and what forces do we have? Virginia upwards, 10 downwards, which is negative, 15 downwards, which is negative, so this is the shear force equation. Here it is also not dependent on the variable x3, so it will be a constant value, meaning for both the coordinate 5, that is for the 5th meter of the beam, and for the 8th meter of the beam, this constant value is minus 11.875 kN. If we want to write the moment equation, well, here's how. Definitely the reaction VA rotates clockwise, again with respect to this polar point clockwise, which is positive on the arm x3. And now the 10 with respect to this moment pole rotates counterclockwise, well now on what arm? Since the entire length of the interval we mentally cut out is x3, and from the beginning of the beam to this 10 is 2 meters, so the moment arm, that is from here to the intersection, is the entire length x3 minus those 2 meters from the start of the beam, which is x3 minus 2. And we write minus 10 times the moment arm, x3 minus 2, and now this 15. It also rotates counterclockwise with respect to the moment pole. So now, on which arm is it acting? Well, just like that, we look at the drawing. From the beginning of the beam to this shear force of 15, we have 2 and 3, which means 5 meters. So the rest of the cross-section, since the total length is x3, then the rest is x3 minus 5 meters. So we write down minus 15 times the length of the arm of action, x3 minus 5. These are things that might be troublesome at first, but over time with the number of beams processed, it becomes more intuitive and easier. And for this long moment equation in the CD interval, we substitute the limits of the intervals, which are 5 and 8 meters, and we calculate the numerical value. And for the coordinate 8, we get 0 kNm. Okay, well, now I would like to show you that it will be much simpler if we go from the right side and write the interval x3 from the right side, that is, from 0 to 3 meters looking from the right side. So if we cut the beam going from the right side and cover its left side, we will have, well, and again, the interval is from 0 to 3, which again is infinitely close to those 15 kN, but we do not see them yet, so we only see this reaction VD. Well, you can see the difference. Here there are 3 forces, and here there is 1 force. These are still simple systems, so maybe it would not be that much easier here, but you can already see that it is easier. And now an important thing that I haven't mentioned directly before, but when we cut the beam from the left side, just like we did in the first 2 intervals, and now the third one too, positive shear forces are upward, normal forces, which we did not have here, are positive from the cut outward, and positive moments are right-handed moments. But when we go from the right side now, we have to remember, we need to be careful. This is very important. And also here at the beginning, most often I think errors occur in this place because we forget about this sign marking. So we need to remember that when we create an interval from the right side, the positive shear forces are those forces that have a downward direction. Positive normal forces are also from the cut, but they have the opposite direction than in the interval looking from the left side. And positive moments are those moments that rotate left-handed. And already remembering that, we can confidently write the shear force equations and moment equations. So the shear force in the CD interval, now looking from the right side, is only, we see this force VD, well, and it is upward. So looking from the right side, it is negative force, which means minus VD. And we substitute, it is not dependent on the variable x3, so it is a constant value. We substitute the ends of the intervals. So for 0 and for 3 meters, it is minus 11.875 kN, which is the value of relation VD. And now we write the moment equation. So this force VD with respect to this moment pole, which is with respect to the cut, rotates left-handed, and looking from the right side, left-handed means positive moments. So here it is plus VD times x3, which is the arm of action. We substitute the ends of the intervals, which are 0 and 3 meters. If we substitute 0 into x3, then the value of the moment is 0. If we substitute 3 meters, it is 3 times 11.875, which is 35.625. And now this 0 and this 3, that's looking from the right side, and this 5 and this 8, that's looking from the left side. So the moment value for the coordinate 5 is at this point, and it equals 35.625. And the moment value for the coordinate 3 looking from the right side is also this point. And this value, writing equations from both sides, must be the same because it's simply the same thing, just calculated from the other side. So here you can also see if we did not make a mistake. Okay, so I hope I have convinced you that it is worth checking at least once from the right side, and not just 3 times from the left, or however many intervals there will be. Because we will simply have less calculation and fewer opportunities to make a mistake, also the key thing is to remember these signs. Now we can move on to drawing the graphs. I will try to simulate drawing the internal force graph. Of course, we prepare an area on the paper for drawing graphs, preferably under the beam. We extend the characteristic intervals and mark the axes. So, I will try to simulate the drawing. It will be easier for you to understand how these graphs are formed when you observe the graphs being created in real time, rather than when I immediately show you how they are supposed to look. So, having already prepared the area for drawing graphs and having in front of us all the values of the cutting forces that we have determined so far in these intervals, we can start drawing the graph. In the first interval, AB, looking from the left side, for value 0 the cutting force is 13.125 kN, and the value for coordinate 0, which is at the beginning of the beam, and for 2 meters is the same, so we connect them, and it is 13.125 kN. We simply connect with a horizontal line, and that will be the first interval, 13.125 kN. It is a positive value, so we put a plus sign, dashed line, and we look further. For the cutting force value for coordinate 2 and for coordinate 5 is also the same, and that is 3.125, well, so it is definitely a smaller value, so it doesn't have to be straight, but the proportions should be preserved roughly. So 3.125, the value also does not change over the whole interval, meaning a horizontal line, and it is a positive value. We dash it, and we have 2 intervals drawn, leaving us with the third. The value in the third interval for here, well, I copied it now, looking from the right side, that is, for coordinate 0 from the right side. It is 11.875 kN, and for coordinate 3 looking from the right side. So the value also does not change. It is a negative value, 11.875, chop, minus sign, dashed line, and we have the cutting force graph behind us. Now, having before us all the moment values that we have calculated so far, we can start drawing the moment graph. I draw positive values for moments below the beam axis. I'd like to see how it is in your department, in your materials strength class, or whatever the subject is called. I know that in mechanical departments it happens that positive moments are drawn above, but in a large part of the fields, rather positive moments are drawn below the axis. So I will draw the positive moments below. So for coordinate 0, the moment value is 0. For coordinate 2, the moment value is 26.25 positive. I mark this value somehow and connect it linearly. It is 26.25 kN. It is positive, we mark it, and we look at the second interval. In the second interval for value 2, it is also 26.25, so the value we already have on the graph for the value of 5 meters of the beam is 35.625, also a positive value, so we mark this 35 and connect it linearly. The value is positive, we mark it, and we look at the last interval also from the right side, looking from the right side for coordinate 0, the moment value is 0, for coordinate 3, the moment value is what we now see on the graph, meaning there is no jump on the moment graph. So we connect it linearly. Positive value, we mark it, and we have drawn the shear force graph and the moment graph. I hope I did this quite clearly and you understand more now. If you feel like it, check out the next video on this topic, link in the description. I will also try to do the exercise step by step there. Thank you for your attention. If you have any questions or comments, feel free to ask questions and leave comments below the video. I also recommend the other productions, encourage you to visit our website, to like our Facebook and Instagram profile, and of course to subscribe to this channel so that you stay up to date with new videos from EduPanda. In the meantime, thank you very much. Best regards, goodbye.